Hello everyone and welcome to this lecture on data communication and networking, and we're focusing on data transmission and want to explore essential concepts that forms the backbone of data communication, including the definitions, the types of the data signals, the transmission impairment, the channel capacity, and encoding techniques. Right. Before you start, as usual, I want you to write something down. You write what you think about data transmission, about the definitions. Then you write down. You Google. You pause the video. You Google. You check if you have done things correctly. You can also wait, maybe finish the video. Then you mark for yourself. So you write anything that you think about data transmission, then you mark at the end of this lecture. All right. So, data transmission, the definition, the process of sending and receiving data across a communication medium. And this can involve a variety of formats. We can talk of audios, we can talk of text, we can talk of videos, right? And the efficiency and accuracy of this transmission are crucial in effective communication. And data can be analog or digital. And we are talking of analog data. This is a data that represents information in a continuous form. This includes signals that vary smoothly over time, such as sound waves from a musical instrument, right? Sounds made by a human voice are also analog. We can talk of a varying pitch of a guitar string produces analog data, which can fluctuate infinitely within a range. Then we can talk of digital data, and the digital data represents information in discrete values, typically in binary forms. We're talking of information being represented as zeros and ones. So a classic example is a digital image where each pixel's color is represented by a binary number. This form of a data is less prone to degradation during transmission, right? So also data stored in a computer memory is in the form of zeros and ones, and this is what we call digital data. We want also to explain analog signal, and this is signal in continuous electrical signal, right, that varies over time, right? For instance, an audio signal from a microphone is an analog signal that fluctuates, right, in amplitude and frequency, representing sound waves as they travel through the air. So I've got a diagram here at the corner. So as the wave moves from value A to value B, it passes through and includes an infinite number of values along its path, right? So a simple analog signal is a sine value that cannot be further decomposed into simpler signals. Then when I'm talking of digital signal, we are talking of a signal that represents information using discrete values, right? So for example, a digital clock displays time in separate distinct numbers, and are preferred in modern communication because they are less susceptible to noise and can be easily processed. So when I was explaining analog data and digital data, I think you noticed something that is got an advantage over the other. You can also see when I was explaining analog signal and digital signal, you can see the best one when I was explaining. Here on digital signal, and right, you can see the ones and the zeros here. So the signal shown here, a 1 represents a positive voltage, and a 0 it is representing a 0 voltage, right? And then also, there's what we call transmission impairment, which is any degradation of a signal during transmission. This can significantly affect the data being sent, right? And data is transmitted through transmission media, which are not perfect, and the imperfection causes signal impairment. So due to the imperfection error that is introduced in the transmission data, the original signal at the beginning of the transmission is not the same as the signal at the receiver end. So there are three causes of impairment that I have here. I have attenuation, I have distortion, and I have noise. And under noise, we also have some types of noise that I'll explain the next slides. So on attenuation is the gradual loss of signal strength over distance. For example, a phone call may become harder to hear as you move further from the cell tower. I can give you an example. When you're on a WhatsApp call, as you move away from Wi-Fi or from the Wi-Fi router, you see that there will be a gradual loss of signal strength. As you move away, it will become harder to hear someone till there is a disconnection, right? So this loss, right, can be due to factors like distance, right, resistance in cables, and environmental conditions, right? So to compensate for this loss, amplifiers are used to amplify the signal. And you can see the diagram on our screen that there is a center here, and this is attenuated message in the middle, and then an amplifier, and then a receiver after amplification. And you can see after amplification, the message from the sender and the receiver are the same. So this is the way to amplify the signal to compensate for the loss for this. And also we can talk of distortion, another signal impairment. And when we're talking of distortion, occurs when the shape of the signal changes as it travels. You can see that this can happen due to nonlinearities in the transmission media, leading to changes in amplitude or phase. And distortion can degrade the signal quality, and it makes it difficult to recover the original information. Here you can check the diagram on the screen. Original signal here red, then this is the distorted signal here in black. So the information here on the original is different from that on the distorted signal, right? This is what. So I can give you an example. A voice may sound garbled or unnatural if the signal is distorted during transmission. So we talk of the change of shape or characteristics of a signal, right, during then noise. This is unwanted, right, signals that interfere with the original signal, right? It can originate from various sources. We can talk of electrical interference, the thermal noise, crosstalk, intermodulation, impulse noise, induced noise, right? And this noise can introduce errors in the received signal, impacting the overall performance of the communication systems. Noise, we have thermal noise. And when we're talking of thermal noise, this is noise that is generated by the random motion of electrons in a conductor affecting all electronic devices, right? So heat agitates the electronic conductors of a medium, which may introduce noise in the media, right? So up to a certain level, thermal noise is unavoidable. And I can give an example, or this can result in static on an audio recording. I think you all know this. A static on an audio recording is caused by thermal noise, right? Then we can talk of intermodulation noise. This occurs when multiple signals mix together, creating interference, right? Occurs if two different frequencies are sharing a medium and one of them has excessive strength or the component itself is not functioning properly. then the resultant frequency may not be delivered as expected. I can give an example from when two radio stations operate closer together. These signals can interfere, leading to poor reception. This is what we call intermodulation. Then there is crosstalk. And when we're talking of crosstalk, we are saying that this is the interference from adjacent channels, right? The sort of noise happens when a foreign signal enters into the media. This is because signal in one media affects the signal of second media. And I also can give an example of in telephone systems, you might hear snippets of conversation from another line due to crosstalk, right? Then we can talk of impulse anti-noise, right? So this noise is introduced because of irregular disturbance, right? Such as lightning, electricity, short circuit, or faulty components, right? The sudden spikes in voltage that can disrupt signals, such as the crackling sound from a lightning strike, affecting radio reception. And the digital data is mostly affected by this sort of noise, right? Then there is induced noise, and this is caused by external electromagnetic fields, such as nearby power lines, affecting data transmission in cables, right? So the noise comes from sources such as motors and appliances. This device acts as sending antenna, and the transmission medium acts as a receiving antenna. These are the three the primary causes of signal impairment. Then we move on to channel capacity. And I want to define the channel capacity, then the theorem, Shannon's capacity theorem. Then on channel capacity, we are saying that the maximum rate at which data can be transmitted over a communication channel without error. Is the maximum rate of data transmission over a communication channel without error, right? So this capacity is vital for determining how efficiently data can be sent, right? So we call Shannon's capacity theory, and this one is a mathematical formula to determine the channel's maximum data rate. And the formula is given there. C representing the channel capacity, which is measured in bits per second, right? B is the bandwidth of the channel, right? Then signal to noise ratio is a measure of signal strength relative to background noise. And the signal to noise ratio is calculated by S over N, S being the average signal power, and N being the average noise power. That's what we call the signal to noise ratio, right? And this theorem also helps us to understand the trade-offs between a bandwidth, one, signal power, and noise in data transmission. All right. So there are factors that affect channel capacity. And I have three here, the bandwidth, the signal to noise ratio, and the modulation schemes. And we are talking of bandwidth. We are talking of the range of frequencies available for transmission. And we are saying that a wider bandwidth allows for more data to be transmitted simultaneously, right? For example, a fiber optic cable offers much higher bandwidth compared to our traditional copper wires. This is our bandwidth. Then on signal to noise ratio, we said that this is S over N, S representing signal power, N representing the noise power. And this measures the strength of the signal compared to noise, to background noise, right? So a higher SNR means a clearer signal, allowing for faster and more reliable data transmission. I give an example of in a noisy environment, a stronger signal is needed to maintain clarity in a phone call, right? Imagine you're in town or at a rank bus terminus, there is noise. So you can see that a stronger signal is needed to maintain clarity, right, in a phone call. So moving forward, we can talk of modulation schemes, and this method is used to encode data onto a carrier wave, and the different schemes can optimize data transmission, right? So for example, we can talk of the QAM that's here, allows for higher data rates by combining amplitude and phase modulation, right? And this affects the overall capacity. Then moving on, signal encoding techniques, right, can also be categorized into analog and digital encoding. And this is the process of converting data into a specific format for an efficient transmission and storage. It determines how information is represented and affects transmission efficiency and influence error rates. And there is analog encoding, which includes amplitude, frequency, and phase modulation. There is digital, where we're seeing unipolar, polar, and bipolar encoding. So here on analog, there is amplitude modulation, right? And in amplitude modulation, the amplitude of the carrier wave varies in accordance with the data signal, right? This is commonly used in radio broadcasting, right? Then in frequency modulation, we are saying that it varies the frequency of the carrier wave. This is used in FM radio, providing better sound quality and resistant to noise compared to amplitude modulation, right? And then on phase modulation, we are saying that phase modulation changes the phases, right, of the carrier wave based on input value to convey information. This technique is often used in digital communication systems. Then on signal encoding techniques, right, when you're talking of unipolar, we are saying that it uses a single polarity, right? The presence of a signal is represented by a positive voltage, while the absence is represented by 0 volts. Single polarity. Then we are talking of polar. It utilizes two polarities, typically positive and negative voltages, to represent binary data. And this allows for better signal representation. So it uses two voltage levels, positive for 1 and negative for 0. Then when you're talking of a bipolar, there are alternates the signal between the positive and negative, right, to represent binary data. This method helps reduce DC bias and improves error detection, right? There's what we call line coding techniques. I have 3. I have non-return to 0, return to 0, and Manchester encoding. And you're talking of non-return to 0, the word itself, right, saying non-return to 0. So in non-return to 0, ones and zeros are represented by different voltage levels. And this method is very simple, but can lead to synchronization issue, right? Then a return to 0, the word itself said that in a return to 0, the signal returns to 0 between bits, which is different from non-return to 0, right? And this helps maintain synchronization, but requires more bandwidth than the non-return to 0. Then on Manchester encoding, we are saying that each bit has a transition in the middle, right? Each bit has a transition in the middle with a high to low transition representing one binary value and low to high representing another. So this technique provides built-in synchronization and is widely used in Ethernet networks. So this one combines clock and data signals, and transition in the middle of the bit period indicates a binary value, right? You also need to look at the advantages and disadvantages of each encoding technique and the real-world application. And this marks the end of our lecture. And feel free to write in the comment section if you have any questions that needs clarification, and comments. If you have any comments, feel free to write in the comment section, and I will look at the comments. Thank you for your attention, and I hope this lecture has enriched your understanding of data transmission. We meet in our next lecture. Thank you.